What's up, Gabe?
What's up, Alex? How are you?
Doing good, doing good. That's
Nice.
good. Let's get started.
Yeah, I have the Google Colab here with me.
Okay, perfect.
Let me see.
So
Are you sharing like a projection?
yeah. I'm gonna share my screen. I have to present a couple of the beginning slides, but then after that, can you introduce yourself? Because there's a couple new people that weren't
Oh
here
yeah,
for the
sure.
meeting, and then we'll get started. So yeah, super excited for this.
Sounds
Let
good.
me share. Okay, guys, so what's up? Welcome to week 5 of the Guild. We are gonna wrap up the kind of text generation arc that we've had in these past couple weeks, where we worked with the RNNs last week, the LSTMs, and then we introduced the transformer architecture. Today we're actually going to build GPT-2 in JAX from scratch, and yeah, really excited for that. There are a few of you that are new, so if you can please scan this Airtable. This is for the INIT Discord, so that whenever I tag the AI Guild members, you get tagged with the information for the sessions, for the videos that I upload on YouTube, and just any resources like the full notebooks and everything. Yeah. And now I'll let Gabe introduce himself, and we'll go on from there.
Awesome. Okay. Nice to meet everybody that I don't know yet. My name's Gabriel. I was the previous guild lead, 2024 to 2025. I currently work at Google, as you may know. I'm on YouTube, work for trust and safety, so a lot of like machine learning engineering. And yeah, I'm super excited to get to this. I want to get started fast just because it's a lot that I have to cover, and I don't want to lose time, to introduce myself. I think this is more important. So let me start sharing my screen, and then let me know if it looks good, Alex. If you need me to zoom in.
That's good. 1 second. Let me quickly, for those of you who don't have the Colab notebook, here's the short URL for it. And yeah, so you guys can code along and everything.
Yeah, so what you're gonna do is you're gonna open this Colab, and then you're gonna make a copy on the top left. You guys have used Colab before, right?
Yeah, we've used this.
Cool. All right, so while we do that, I'm just going to give a quick rundown of what's going to happen. So if you've never coded in JAX, I made this notebook to be very similar to like what a PyTorch like training would look like. And then if you don't know PyTorch, just bear with me. I'm pretty sure this is going to be somewhat understandable if you know what a neural network looks like. GPT-2 is divided into multiple subsections, and we're going to go through each of them. Essentially, what you have to do is just run this first cell, and then we're going to go and install a couple of utilities. Oh, I forgot to say, before you do that, make sure to swap it to a TPU runtime over here on the top. So I'm going to change it to a V6E1 TPU, which is the Trillium. And then you have to just rerun everything. I decided to do checkpointing on my Google Drive just because it's easier. Also, Alex, let me know if there's questions in the chat, and then you just like interrupt me, and then I can answer.
All right, perfect.
So what this is doing is just importing all of our earlier stuff. Like we have Flax for modeling the neural networks, Optax for checkpoint for optimization, Orbax for checkpointing, and then the data loaders and some like utility functions as well. I decided to connect to my Google Drive because I'm going to save my checkpoints here, my model checkpoints, because you can then just import them wherever you want. And the data set that we're going to be using is this really popular data set. It's called, share this tab instead. Let me see. Can you guys see this other tab here? Sure. Let me see. Split. Here. Okay, can you guys see this tab here, Alex, with the data set?
Yeah.
Okay, sounds good. So this is what it looks like. It's literally just text. The thing about text training is that all you have to do is literally give it loads and loads of text, because every single new token in this sentence becomes a classification problem. It's given this piece of text, what is the next piece of text that I should predict? And if you do enough of that, and trust me, like you have to do a lot of that, then the model starts speaking like actual English language. I trained the model overnight, like on Saturday, and it ran for about 8 billion tokens, and it was pretty good at English, actually. I think last year when we tried to do this, it wasn't as good because we just didn't give it enough data. This data set has the 8 billion tokens that we want. But GPT-2 was trained on 40 billion, so it would have taken like another 5 days. Anyways, so if you load the data set here, you're gonna just like use like the standard Hugging Face data set. This is gonna take a bit, so I'm just gonna like wait while this is downloading. And then if you're running this on your end as well, you can just hit play on all of the other ones as well in advance. And then we're gonna use the GPT-2 tokenizer, which I'm pretty sure Alex must have covered the tokenization stuff. Or
switch your screen.
Oh, yeah, sorry, through this tab. So if you just run the data set here, it's just going to take a little bit because there's a lot of different like folders to download. The tokenizer is a thing that splits the text into the chunks that we want so that the model can speak in those chunks instead of like character by character or word by word, because word by word is kind of like, it's not the real use of like, it's not how we do text. We have like different sections of text. We don't have like, I can only speak this word and then this word. We can do like a word, a part of a word, and then a combination with a different part of a word, and that's easier for the model to understand. So here, I'm gonna basically, once this is done, which is gonna take a little bit, you basically just ask it to write a random sentence, and then it's gonna tokenize it for you. So what that looks like is I'm just gonna say like, oh, pancakes and bananas, whatever, and then you're gonna see like a bunch of numbers representing, like a sequence of numbers representing that specific sentence that I said. And that's how the model actually understands text. We're going to grab that sequence of numbers, and then each number has its own like vector representing it. And that's how we like first embed the text. This is called the embedding. Now we're going to be using GPT-2, 124 million. So overall, everything that's trainable in this model, there's like 124 million of those numbers that we're going to tweak with gradient descent. And trust these configurations here, they're going to add up to 124 million at the end. But essentially we have the sequence length, which is how much text it can like read at once and also like produce later. The vocabulary size is like how many total tokens we have. So we're never going to see like a tokenizer output a number 50,258. There can only be up to 50,257. And if it doesn't know a certain like part of text, it would just like split it like into like smaller chunks that it knows, you know. We're gonna have 12 transformer layers. I'm gonna go through what that is. Each transformer layer will have 12 attention heads, and the hidden size will be 768, and then but the MLP hidden size will be 4 times that. I'm gonna also explain what that is. So breaking attention into blocks while the thing is loading, just so I have like time to explain everything. As you may know, attention works in this like really complicated process of first you have to like embed your text, and then you have to like compute some sort of like relatedness between the queries and the keys using the dot product, and then you have to like contextualize that with your vector, and then you normalize it, and then you add that to like a big MLP so that you can like store facts, and then you like predict the final softmax probability of like what the next token should be. I can show you how the softmax function looks like, but essentially our tensor formula is the QK divided by the square root of D times V, which I think we talked about it but Alex must have talked about it last week. And then Alex, if you need me to contextualize something a little bit better, let me know, since I wasn't here last week. But essentially these are the blocks. We have the attention, multi-head attention we call it, because there's multiple different like parts of searching for the right key and the right query. We just split that up. And then we have the feed forward, which is sort of like an MLP. That's the thing that I said that we have like a hidden size just for the MLP. It's because it's going to expand our hidden stream, which is like that vector that we're updating constantly. And then finally, the softmax is the final layer that predicts the answer. For multi-head self-attention, this is how it looks like. Essentially, we have the keys and the queries and the values. We're going to compute the dot product between the keys and the queries, which are just names, honestly. Like, we give these names because of what's happening to them and not because of what we decided they're going to be named. It's really like, oh, I know that I'm using these keys to find some similarity with my queries. So I'm going to like just call them keys and queries. It could have been the other way around, you know, like it's just whatever is happening to them is what we decided to name it. And then the values is some sort of like weighted average of those probabilities of that dot product. You're going to see this in code. It's going to be a little easier. And that is just a subsection, this part here, of attention, of the transformer, sorry. So this part here is this, everything that's happening inside of each head is this bigger square here. So we're going to do this for every single head. And then we're going to just like concatenate everything, join everything. And then I'm going to pass it through the MLP after applying like some normalization so we don't like explode gradients and stuff. So the data set finished loading. I'm going to just like write pancakes and bananas. So this is my sentence, right? 47, 1,192, 1124, 290. But the model will understand this because every single one of these numbers has a predefined vector or something that we're going to train so that it can understand this sentence. And then let's get started with the coding. So first that we're going to do is, actually, I'm going to start with the multi-layer perceptron because it might be, just so you get familiar with the JAX syntax. And how it looks like is we have to define these weight matrices here. So this is our MLP. We have the first linear layer, an activation function, and then a second linear layer. You can see that it expands the size of the token stream. Token stream is just everything that's like going up this arrow here. This is called like a stream. But this is a vector of size 768, like we were saying, and this one here is 4 times 768. So we have more representations and more like variables to represent things. How we do this is we first have to define these 3 things as part of like our initializer. And so what we call these layers like a fully connected layer. And the way that you do this in Flax, which is a part of JAX, is you just define a linear. It's called linear layer, you see? So you do linear layer, and then I have my config. Remember that we have like a hidden size and the MLP hidden size. And then I'm just going to pass in some random number generators so that it initializes our model weights like randomly. And then we also have the other one, which is the same thing, but it's just swapped hidden size, because we're going to go from the MLP size to the actual hidden stream size. So it's the second square here. So second trapezoid. And then now we're going to pass our X, which is our stream, through these matrices. So the way that you do this, you just go, oh, I'm going to grab my initial X, which is of shape batch, sequence length, and hidden size. Batch being how many examples there are, sequence size being like, sequence length being like all of the tokens in my sentence, and then hidden size being the same as like D model. There's a couple of like different names for it. I'm going to treat hidden size as the stream dimensions. So since we have like a vector that we're going to pass and update through our stream for every single example, for every token in that example, in the batch, right? We're going to have our input X be have this like 3 different logical dimensions. So it would look like something like this. We have like, this is an array, right? 1, 2, 3. Let's not say 3. This is a batched array. And then let's say that every single one of these numbers is a vector themselves, whatever. So this is how we have like our array being passed to X. We have like multiple of these nested arrays. And then, but what we reference them by is just like these logical names like batch, sequence length, and then hidden size. So what we do now is we override this method called call. And then on the call method, what we do is we first pass the X through our fully connected layer, the first one, and then we're going to apply a jelly linear, our nonlinear function, so the activation function, and then we do the second one, and then we just return. This is our multi-layer perceptron. It's a very simple code block, and it's very like dynamic. We can just pass whatever config we want, and we're going to have a 2-layer multi-layer perceptron that's going to like input and output from the same vector size to the same vector size. It's just having some sort of like expansion in the middle of it here with some activation function. This is what they did for GPT-2. Now we're going to get into a little bit more complicated part. I want you to bear with me here. If anything goes unclear, Alex, I'm gonna trust that you can like help debug this, whatever is the like. If anything is complicated for them, like in terms of like what's going on, I'm gonna assign you for that job just because I don't want to run out of time before we finish this. But essentially, we have to define another set of weight matrices here, right? In attention, we have 3 different weight matrices and the final output weight matrix. And we're going to call them WQ, WK, WX, and then WO as well. WO. The way they do this is you go and say self.WQ equals and then x.linear, whatever, right? And we're going to do this 4 times. So we're going to have WQ, WK, WX, or WV, sorry, WO. The problem is, since we have these heads and basically our input is of size B and H, what you have to do also is you have to make sure that you can split whatever is in your hidden stream. So let's say that my hidden stream is H is 768 dimensions. You don't have to copy this. Every head split into how many heads we have in the config. We have 12 heads. So into 12 heads, this is 768 divided by 12. This is 64. Every head sees H equals 64. So when we're passing this through the attention call, we have to rearrange. And what this rearranges is a very really nice notation, is that we can literally expand our matrix into this shape. So what this looks like is we had originally B and H, batch size, sequence length, hidden size, but I'm going to denote this as H being a product of heads and every single head's dimension. So this is 60, we have 12 heads. Oh, sorry. We have 12 heads and then 64 here. This is automatically computed because it knows that this is 768 as H. So we just have heads and D here. And then it sort of like rearranges our tensor for us, and it becomes a 4 times nested list instead of a 3 times nested list of batch, sequence length, hidden stream. It becomes batch, head size, number of tokens, so sequence length, and then every single head's dimension is called D, right? So that's 64. For that, we have to find out how many heads we want. I said 64, but I have to actually compute that. So number of heads is number of heads here. And head, that's what I did. Head. And then we have the head size, which is that thing that we have to compute, 64, right? Head size equals config.hidden size divided by config.endHead. We can also do self.endHead. The output size is the same as the hidden size because some people like to do another MLP after the output, but we're just going to keep the same stream size across all the layers. And then the hidden size, obviously, it's the same thing as the config hidden size. A nice assertion to add here is that you have to make sure that your hidden stream size is divisible by all the heads that you have. So we have to just say self.hidden size must be divisible. This is how you say if it's divisible, right? Equals 0. H must be divisible. by X. So if it fails, we have that problem, right? And now we have to define how we're going to call that weight matrices, right? The same thing that we did before. We just say, what is the input and what is the output shape, right? So the input shape is we're going to see our X, right, which is the hidden size. And then the output is the hidden size as well. So we're just going to have this like output the same size. It's kind of like it just changes the representation of X. It doesn't like change its size. I'm going to say use by it. You don't have to worry about this. I'll just recommend it. And then our RNGs for defining the initialization stage. And then this is literally identical for all of them. But what's happening here is we're converting each. You're gonna see that we're gonna call each of these weight matrices on top of our X. So each of them will assign kind of like a function to that thing, and that will become the QKV, because our X comes from QKV, right? If you can see here, we multiply X by these three matrices, and then we get QKV. And then now, before we like rearrange it into the heads, we can sort of like compute them all together. And we just say like Q equals self dot WQ X, K equals self dot WK X, V equals self dot WV X. Really simple here, right? We grabbed our X, which is a size, batch size, sequence length, hidden size. We just multiply it by our weight matrix, and now we get another batch size, sequence length, hidden size, but each of them has their own function. One is the query, one is the key, one is the value. So when we backpropagate this to train this with gradient descent, now our weight matrices will give more and more informed keys and queries and values. So that's why we do this splitting here. And then, like I said, we have to rearrange them. I wouldn't have you have to do this because it's kind of like a thing they've never seen. But it's a really nice utility function that I can just say, oh, figure out for me what size is the hidden stream, and then just split it between heads and the size of each head. Now we have to compute the dot product, right? The attention probabilities, which is telling us how much each query position pays attention to each key position. So it tells us where information moves to and from. So this is really important for text, because we want to see what every word in my sentence correlates to every word. So we want to see like how much every word correlates to every word. Now we have to compute the dot product, which it looks a little ugly, but at the end it's just going to be like a matrix multiplication, as we call it, like matmul. First, I have to also define that little square root of d here, just so I can multiply it right after. So I'm just going to say that our scale is what we call it scale, which is 1 over square root of d. It's just going to be the head size elevated to 0.5 negative, because what this does is that it's, you guys probably know this, right? If it's negative, it becomes like a ratio, and then if it's 0.5, it means a square root. So it's like scale head size. This is what we're multiplying it by, right? So I just set the scale to be elevated to negative 0.5, and then it's going to understand that it's multiplying by the square root, the inverse of the square root. And then, okay. Now we're going to do some sort of rearranging just because we need to. You don't have to focus on this part. We're just going to rearrange the keys to have shape. So right now, if you remember, the shape is B heads and D, right? I'm going to convert it to B heads DN. Just because our matrix multiplication, it only operates on the last 2 dimensions. So if you have a square matrix that has like batches and it has like sequence length, at the end what you're going to see is the 2 logical dimensions of how many tokens, and then what's the size of each embedding for every token. And it looks like this. It's just rearranging these 2 here so that we can operate on them. And then now we're going to calculate the attention weights, which is that stage here. To show you the attention probabilities, attention weights is the same thing. It's just before or after a softmax. So the attention, where is it? The attention weights is going to be a map mold. JMP is like the JAX numpy. And then we just do K key, KQ, and then multiply by the scale. So it's this inner part here before multiplying by V or softmax. These are our weights. And then now we're going to have to define a really important part of this, which is our mask. Why do we want a mask? So when we're working with attention, when you're generating a sentence with a language model, you're obviously not gonna be able to know what's the token that I'm gonna say after the current token. But when you're training, we actually have to encode an entire sentence and then have the model predict every single token's probabilities. So you do have access to like all the other tokens, but we don't want to tell the model about those other tokens. We want it to sort of know only the next token based on the previous tokens and not any token after that. So what that looks like is, let's say that every single column or row here is a token in a sentence. So let's say apples, bananas, pancakes, whatever. And then in here would be apples, bananas, pancakes, whatever. We only want to give the model access to these ones that are highlighted. We don't want apples to see bananas. We don't want bananas to see pancakes. So we don't show it, if that makes sense. And that's the way that we do this is, as you can see, this is there's a triangle in this matrix here. So in JAX, there's a really nice way to do this. That you can just say, give me a triangular lower matrix, which literally just looks like a lower triangle on this matrix. And just give me that matrix of the size of my sequence length. So for every token, right? So we have n tokens, which is the same as sequence length. And then I'm just going to define a square matrix that has ones across these little triangles. And in case we don't want actually a one, we just want them to be Boolean, because you're going to see that we're going to do a little function that sees whenever we see a true, we actually compute the attention. And whenever we see false, we don't compute the attention. So what that looks like is we're going to finally calculate the attention weights based on that mask. We call them causal masks because we only look at causal tokens, the tokens before the current one. And you're going to see that every single thing that is not false will be used, but every single thing that's false, we're going to be converting them into negative infinity. So the model really does not look at those tokens. There's not going to be any weights. There's a GNP where causal mask. So wherever I see a mask being false, attention weights are going to be converted to float negative infinity, like this. Attention weights equals JAX dot and then dot softmax. Now we're doing our softmax part. And I'm using the cheat notebook here just so I don't have to make any mistakes before. So this is what this is doing. The softmax is, and I'm telling it to figure out which axis to do. When I do -1, you just say figure out which axis you want it to run on. The softmax is this stage here of the formula, softmax. And then, I guess this here. And then the output is just contextualizing it with the vector of values, right? So we're just going to matmul again. Matmul, attention weights, and V. And then we're going to merge our heads back because currently we have this shape here, B heads and D. And I want to return, remember, B and H. So we're just going to do another rearrange. So out equals rearrange our out vector from B heads and D to B and heads So what this is doing is telling it, oh, infer for me what this shape is. I know it's going to be the same shape as what we had in the input. But it basically figures out how to do this rearrangement for us. And then at the end, we just multiply by the output weight matrix, this one here. There. This is our attention block. And I added some type checking in case there's any errors. We're going to find out what's wrong. And now we're going to integrate them both together. We have the attention weights, and sorry, we have the attention block and we have the MLP block. And now we have to make the transformer block. The transformer block, it looks like this. We have to first add a layer norm on our X. We pass that through the attention. And then we add the hidden string to itself. This is called like a residual connection. I'm sure Alex can mention this later. And then we do another layer norm on that result, pass it through the MLP, and add it back to itself, another residual connection. This is very useful for avoiding the vanishing gradients problem. So our transformer layer, it has multiple blocks, right? We have the attention, which is multi-head self-attention, big RNGs, same thing. We have the MLP, which is the multi-layer perceptron, config RNGs, and we have the two layer norms. And next, the layer norm, literally very modular. Like you can see how GPT is very modular. I'm just reusing things that I define as part of blocks. And now we have defined the call method, right? Which is that pipeline that I was showing, right? First, we do the layer norm on X, and then we calculate the attention, add it back to itself. So I'm just going to go through this really quick. So we have to add it back to itself, or I can do this slower. Let me see. Oh no, I have to do it in the same block. Self.attention. We call the attention after calling self.layer norm 1. So what this is I first called this, then I called this, and then I add it back to itself here. And then I do the same thing with the MLP. And then the second layer norm. And then we return X. That's our transformer layer. Again, very modular, very like reusable. If you look at this diagram, you can totally do it yourself. And then now we're going to integrate everything, right? So GPT-2, it has a couple of other things as well. It has our embedding table, which is the thing that I said that reads off of numbers and converts them into vectors. I put them here myself just because I didn't want to have to explain the nnx.embed and the positional embedding. Positional embedding is just on GPT-2, it's a learned embedding, which means that GPT learns to encode position as like a latent vector as well. In the transformer paper, it uses a sinusoidal position encoder, and you can look up later what that is. But GPT-2 specifically does this thing called like the word token embeddings and the word position embeddings, the WTE, WPE. It does it standalone. So the layers now we're going to define, right? I said there's multiple layers. So every single transformer block is connected to another transformer block, and then we finally have the output at the end. So our residual stream is going to literally loop through all the layers that we have. And in fact, we have 12 of them based on our config. So I'm just going to define our layers here. It's going to be as like a big list comprehension of a transformer layer. Transformer layer, config, RNGs, or range config.n layers. What is this doing? It's creating a transformer layer for every single, like 12 transformer layers. It's making a list of transformer layers, basically. And then we have a final linear layer norm at the end, actually. So layer norm again. Oh. Another layer norm. And then now we have to call our model. right? What do we receive? This time, we don't receive batch size, number of tokens, hidden size. We actually receive just this. We receive something like this, obviously batched over, so there's like multiples of these, but we don't see any hidden size here. Why is that? That's because we haven't embedded this text yet. All we have is the input IDs, and then our embedding tables will compute the hidden size from the input IDs. So essentially, our positions here, our input IDs are here. So we're going to receive batch size and sequence length. And then our embedding tables, we're literally just going to pass our input through them and just like sum them here. This is to get the, oh, sorry, not input IDs. I don't have an X here. Good to make it less confusing, actually. And the positions are basically, since the positions are going to be looking something like this, so 1, 2, 3, 4, 5, 6, 7. We're going to train an embedding table that's going to read one and it's going to say, oh, this is a vector that I know. This is a vector for this position, for this position, for this position. And we just literally just going to add them together. So we have both an encoding for the positions and an encoding for each token that in that position. And then we just add them together, and then we have a vector that knows not only the word, what it means, but the position that is in the sentence as a single vector. So we just add them both together. And then now we're going to have to pass our hidden stream. Sorry, now we have something on the shape of B and H, right? This is B and H already. Now we're going to pass this through our hidden stream. So we're going to go literally 4 layer in self.layers. It's that simple. We literally just for loop all our transformer layers, and then layer X. We just pass X through that layer, and then we just X layer norm final like this. And then we bring back the logits to, so now this is gonna, the logits are gonna have the shape of our, let me see, it's gonna have the shape that it did, I think, on the start. Logits, that's still gonna be. Okay, so it's still gonna have B and H. This is what we call logits, right? It's the final output of the model before we do the softmax, which is the thing that like tells the model to pick that specific token, because it's gonna like make all the tokens in all the logits add up to 1, so it's like a probability distribution. And then we're just gonna grab the most likely one, and then we're gonna use that as the next token for our model. So this is our code here for calling GPT-2. That's it. We're done here. Now we're gonna actually generate a sentence with it, and hope to God this is working. I'm pretty sure it should be. So I'm just gonna create a dump model, and we're gonna generate text with it. So I said the quick brown fox, and then it's supposed to return jumps over the lazy dog. Oh, I think let me see, tuple argument. Canon class shape. Did you write JP once? I think I did a mistake somewhere here. Oh, I see. JP once. It was a very dumb mistake. Let me get the matrix here. Okay, here. Sorry. Yeah. Oh, the same error. Interpreting argument as an abstract array. Which argument? If anything, I can just copy over the code I had on the other notebook, just so we don't lose this for the purpose of the demo. So I have the multi-head self-attention here, multi-layer perceptron, the transformer layer, GPT-2, our generate function, I don't see any differences. Let me see. It's going to run through everything again. There, I think it's working. Yeah, I think it was a very small typo potentially that I had, or some like text that I left. But essentially now the model is autoregressively, and autoregressively means every token is generated once. So we do a full pass of the model for every single token. But it takes a little bit, even if we're working on a TPU. But this is a random model. So every single parameter in the GPT is like model is basically random. So it's not actually like a good model. It's just gonna generate jargon. And now we're gonna create the training loop, which I already implemented everything here. We just have to create the loss function and the optimizer. So here it generated the quick brown fox, Sinian, nin, chef, relative, bears. So, you know, like I told it to generate up to 20 tokens here, and it generated just absolute jargon, which is the funniest thing. I think activity for you guys, you should try to get different checkpoints of this model during the training and see how smarter it gets. But there's going to be some really funny iterations that it's just going to tell you absolute jargon, but it's going to say jargon, but it's going to sound like English in those intermediate steps. So you're going to be like, it's trying to tell you something, you just don't know what it's trying to say. Okay, so our training loop is just going to be controlled by this like optimizer schedule. You don't have to do the schedule, but essentially we just use this little optimizer that's famously known for being really good. It's called atom weighted, like this. And then we just pass the learning rate equals schedule, and then the weight decay. You don't have to worry about this. And then we create an optimizer in the next optimizer. We pass our base model to the optimizer, our dumb model, and then just say that we want to optimize everything that's a parameter. And then we're going to batch our data set. This thing usually takes a lot of time. So I will not be running the full train loop on. So let me have to create like 1DB authorized. 1 second, guys. I have to get my 1DB key. And if you guys have ways and biases, this is for like the monitoring of your run. Oh, sorry, use an existing here. Okay, so it knows it's me now. It's going to log the training. We just have to implement the loss function. So a loss function for a language model, like I said, is literally just the next token, right? So we have a text and we have the tokens prior to that. We will just tell the model, hey, given this previous text, your label is the token that comes after this. I'm just gonna run through this because we're running out of time. Alex can explain this later in a different session. But essentially what we do is we have our loadeds, which is whatever the model output up until the final layer. Up until the final second to last token. And then our targets are whatever, let me rephrase that. So our loadeds is when we grab the input IDs, which is our sequence of tokens, right? Like remember the pancakes, whatever that I did here on top, 47. This is our input IDs. Our target for this guy is this guy. Our target for these two is this guy. Our target for these three is this guy. So I'm going to call the model here to get the loadeds, and then I'm going to set this as a target. And I'm going to do that for every batch. Oh, did I? Let me see. I think did I copy an extra? Let me just make sure I didn't copy this twice. Oh, we don't have to do this part. This is just repeating. Okay, I accidentally repeated the train step here. Blah, blah, blah. Okay. I think this train step goes here. It's the same. Okay, so I just accidentally copied everything twice here. Okay, perfect. So we're gonna grab those tokens all the way up to the second to last, call the model with that, and set our targets to be the one right after. So the one at the end here. And then our loss is a cross entropy loss. You can look up what that is. It's literally just saying whatever our logits distribution, you're gonna see that it's like a distribution, to be as close as possible to the target distribution, which is like 0, 0, 0, 1, 0, 0, 0, 0 as like a one hot encoding of the one being the target, right? Like the position of that token in the vocab. We just get the mean of that across the batch, and then that's our cross entropy. Once we call the model, we call the loss function on the model, JAX, it looks like this. You get the value and the gradients, the value of the loss and the gradients of the loss. And then we just optimize the model based on the gradients of the loss and the model itself. And then this is calling our metrics, like our 1dB weights and biases. And then we return the loss. Very convoluted. I'm sorry that I'm having to rush through this. I wish I could spend more time and do a full lecture. It is a work day for me. But Alex can run you through any questions that you may have. But I would really just want to see this running for you guys. So our check pointer is something that I'm going to use Google Drive for. So I'm essentially just like telling it to store all of my checkpoints in my Google Drive. And that's where the fun thing is going to happen, that I'm going to skip this part here. And I'm actually going to load our model. Model equals load checkpoint. This is the part that takes forever, the training loop, right? This part takes at least 4 hours. And then this part here takes about 8 hours. We're gonna skip that part because I already have a train checkpoint. And then hopefully we'll see a model generate what the meaning of life is. And we're done. I wish I could have taken more time on each of these individual steps, but so our checkpoint was restored. I trained it for 50,000 updates. So every update is every time that I compute a loss and I update my model based on the gradients. It's like a gradient descent step. So I had a gradient descent step 50,000 times. And that took 8 hours on these TPUs. That's how you know, like, even though it's a TPU, like it takes a lot of time. I know people do multiple optimizations. Like I didn't like distribute my model. I didn't do anything like crazy here. This can be done in 5 minutes if you're a very good engineer. Like that knows like distributed models, everything. I don't want to like overcomplicate things. So it said that the meaning of life, and this is me, everything else here was the model, is that we are all in the same place. We're all in the same place. See, it's still dumb, but it talks in English. And that's really crazy. Like we can tell the model to generate more. Let me see max new tokens. Maybe let's do 100. But this is going to take a lot of time. This might run out of RAM because we don't have something called KV caching. So every new token that I add, it's a quadratic, it's a quadratic cost to my model generation. And that's the point of the KV cache, is that we're not recomputing this part here for every single like new token. So it's not quadratic anymore. The attention is the most expensive stuff. I think I'm going to wrap up here. I'll leave like 3 minutes for questions, like, and yeah, just like high overview questions if you guys may have. I know this is a little convoluted. Alex can run you through this. I think you have like another half hour of like just the AI Guild lecture. So yeah, we're just gonna wait for this to generate, and then yeah, Alex, how does it look? Oh, wait, you muted. Alex, you're muted. Sorry.
I'm just asking them if they have any questions.
Okay. So anything I can help with to clarify?
They're all good, Gabe. Just asking if we're gonna post this on YouTube.
Yeah, for sure. This is gonna be in YouTube. And yeah, I'll let you guys run through this collab. You have the full copy, right? Oh, if anything, I think the link that you shared with them at the start is now updated. Because if they made a copy, oh, they can't edit this. So I think the thing that you see on your end is the finalized notebook, and then you can even train this yourselves. If you guys want to reduce the number of steps, you just divide this by like 1,000, and then this one here divide by 1,000, and then it's gonna like finish a lot quicker, or 10,000. Just so you can see like intermediate steps. Feel free to have fun with it. But yeah, thank you guys for listening in. I hope this made a little bit of sense. If it didn't make sense, I would totally recommend you to watch the three blue one brown video on Transformer. It runs you through this like detail by detail, like every single of these operations in math and like visualized. Here I'm oversimplifying. Like this step here is, it should be very like clear in your head what it's doing, but I'm sorry that I can't give you that vision yet because I don't have much time. But once you're familiar with this is going to make so much sense, I promise you. If this was a little too complicated, don't give up on this. I tried to make this as modular as possible. But yeah, I hope at least the MLP made sense, right? We have like the two linear layers and we just call our hidden stream on this sequence here that we're making. If that didn't make sense, just ask Gemini to help you out, or Alex. Alex is the goat. So yeah. Well, thank you guys for listening in, and thank you, Alex, for letting me present this one.
For sure, bro. Thank you for coming and presenting it.
For sure. All right. Let me get going now. I think it's lunchtime. I have a meeting right after. So
Look, I'll put it something.
oh, really? So the meaning of life is that we're all in the same place. We're all in the same place. Oh, it's still repeating. This happens. It happens a lot.
Yeah.
But you can see here our total parameter count is 124 million, approximately. So that's exactly the model that they made. It's only they trained it for longer. So you do have to like keep the loop going. But anyways, I'm gonna get going now. It's been a pleasure. Hope to see you guys again in a different lecture. Maybe the wrap up, it's next week.
Yeah.
All right, so maybe I show up in the last one and just to show face and not to present. All right, I'll see you guys. Take care.
All right. Bye. Thank you. All right. Let me know. I know it was a little quick. Let me know if you guys have any questions about any step along the way. I'll explain any little thing. So I'll open up this JAX, like the notebook. This is the one from scratch. Just ask me any questions about any bit that you were confused on. Again, I know it was a little quick, but especially if you have a question about why anything is being done. The intuition is more important than the actual like writing of the code and all that. So again, anything, literally any little thing, just let me know. The attention diagram? This one right here?
That one and like the first picture.
This one? Or, oh, you said the first picture.
No.
This? Okay, so this is the official like architecture from the original Transformers paper. There are a couple things that are different. So for example, the original Transformers paper came out in 2017. GPT-2, that's when they started using it for actual text generation. That came out like around 2021, something like that. Just backstory on all this. The whole point of the transformer architecture and attention was because we had these text generation models before. They were called RNNs, but they had this problem that they would really forget things as they generated more text. So for example, if you write out like the quick brown fox, and then you start like generating jumps over by the time it gets to this point, it forgets that it's talking about the quick brown. So it starts, generating still English, but not anything sensical. I mean, at the end of the day, kind of what you saw, what the model was doing, since it wasn't trained for a super long time. There was that problem. And also, since we're generating each text one by one, it takes a long time to train. And at the time we had like all these GPUs and everything. So we wanted to make training a parallel task, right? That you can train different batches at once. Those were two problems. Then came this transformer architecture, basically the backbone of all the LLMs you see today. However, you see how we have two different kind of blocks.
Yeah.
One of them is called the encoding block, and the other one's called the decoding block. The whole point of the paper was that they wanted to find a better way to translate things. So they didn't even think how crazy this could get, to create all these LLMs. So we had the input embedding being English. So that encodes the English language in some kind of latent space that the model understands what it means. And then it decodes that into French or German. What OpenAI basically banked on was that, okay, if we completely rip apart this encoding part and we just work with decoding, we can make a model that speaks to you, that you could have a conversation with. And if we scale it up, they banked on, okay, this could be something really good. This could be something really crazy. And that's when they went with GPT-2, GPT-3, and then obviously everything we have right now. What the bet they made ended up working. But this is essentially just the same thing you're seeing, right? This is a transformer block. You see the transformer block is made up of two little things, the multi-headed attention and then the feed forward. We repeat that n amount of times. So that's like the transformer layer. We could have like 6 of these transformer blocks. The output of one becomes the input to the other, except here we just kind of transfer it to this other block, which will decode whatever this encoded to translate it to French or, whatever other language. So for example, here, I think there's a better diagram. This is a transformer block. Yeah. So this is all of that going on. The same thing you saw in the official diagram. Just, we literally built all of this kind of, I don't know, think about like little Lego bricks, right? We built the transformer part first, and then we built the MLP, then we kind of attached them together. And then to have a whole architecture, we put multiple of these transformer blocks together. Yeah, if it wasn't clear at first, again, just to have a high level intuition of what's going on, the attention blocks, what the attention blocks basically do at a high level is it creates a contextual awareness of a sentence. So if I tell you, I use this example a lot in the Wednesday meeting. If I say the sentence, she went to the Apple store, she bought an iPhone, you know what Apple I'm talking about. It's not the fruit. So the whole attention block, it looks at the whole sentence, right? And it looks in a mathematical way. This is learned through a lot of training. It basically looks for the words that give context. So in that sentence, she went to the Apple store, she bought an iPhone. The word, token, iPhone, would have like a really high value there, right? Because that tells you that the apple is not the fruit, apple is and then same thing with the store. No one really says, I'm gonna go to the Apple store. I don't even know if they have those, like just a store that's just apples. So that tells you a lot that Apple is the tech company. That's what the attention block at a high level does. it kind of learns the contextual awareness of the sentence. The MLP block, you can think about it as actually learning like what the sentence means and learning the new contextualized sentence. You project this. You see how we went from the dimensions of the model, which was 768, if you remember. We basically project that into a 3,000 dimensional or 3,000 dimensions. Basically, just think of going into a higher dimension that the model understands more relationships between different things. It stays there, and then it just projects it back into the model 768 dimensions. And every step is that. Let's learn the context of the sentence, and then let's learn what it means, and then pass it on to the next one. You can also think of each attention head, because you know it's multi-headed. We have different attention heads. Each head focuses on a specific part of like the sentence. So maybe one of the heads learns to look for grammar. Another one of the heads learns to look for punctuation, things like that. Like capital A Apple in the middle of a sentence is the tech company. You wouldn't put a capital A for the fruit. Things like that. We attach a lot of layers and it learns.
About the heads, how can I like visualize what the heads are?
Visualize what the heads are. So the heads, each head is this. Each head is, I don't have it coded here. Do you want me to code it? It's the same thing we saw. Each head is 3 different weight matrices that we have. We have the query weight matrix, the keys weight matrix, and the values weight matrix. It's a bunch of, that's where we do this equation. So we multiply the queries and the keys. You could think of the queries and the keys being kind of like in the same, let's use the same example. For the word apple, I guess, think about it asking, okay, I'm the word apple, what word tells me, or what word describes me well? Something like that. The key would be the iPhone part saying, hey, I'm the iPhone. I describe you pretty well. Like I tell you, you're not the fruit. I tell you, you're a company. That's obviously very, just a big analogy. This, in a mathematical sense, of course, it's hard to really visualize it. I would suggest actually go to the Wednesday lecture video and you see kind of the way that the math works. But again, most important thing right now, intuition. That's what's going on here. We apply this to a softmax. So this gives us a probability distribution. That scared me. It gives us a probability distribution. That's what the softmax does. And then we multiply that by the values matrix. You could think the value matrix as telling us, okay, this, whatever you got here, this is the actual information of that. So the query is saying, I'm Apple. Does anyone describe me? The key says, okay, I'm an iPhone. I'm the word iPhone. I think I describe you pretty well. And the values is like, yeah, you guys are related, highly related. What you get there is basically a distribution of, okay, words that are related, words that aren't related, things like that. And when you pass that, do you know about embeddings?
Yeah, it's like vectors.
Yeah. You can think of, well, I'm gonna draw on the board so that the video could see it, but if you want to see it, like just move over here. Just a very quick thing, right? We have the word, let's keep using Apple. Can you guys see from here?
Yeah.
Okay, we have the word Apple. You can imagine when we talk about 760 dimensions, literally think of well, you can't think of that, but think of a room that it's stored in. And let's look at it in 2 dimensions. Apple has an embedding that points it this way. So now we know, like, okay, the word apple or whatever. Whoops. So then what attention does is, and the positional encoding. You saw how at the beginning, before we applied all the attention, we checked the positional encoding and then we added it. What that does is that the positional encoding, like I said originally, it kind of just tells us the position of the word or the token within the sentence. So you can think about it as kind of slightly moving, depending on the context, kind of moving the embedding a little bit over here, whatever. This is the new embedding. And then just think about after attention, after applying attention and everything, if you remember in the residual stream, I want to show you this part. This is really important. Okay, this is the tension. You see how we add this, right? We add the input X, in this case it would be Apple, to whatever happened in the attention block. So think about the attention block basically telling us, you can imagine this part of the thing being the fruit section. So you see like bananas around here, whatever. The attention block tells us, okay, we aren't, like I realized we aren't talking about the fruit. Let's move this vector over to wherever like the tech companies are. You can imagine, and I think it's a really good explanation of that. So a good way to visualize that. And now we have our new Apple embedding. We updated it. We did X, the original embedding, plus the change of X, right? You can imagine the change of X, what attention does is it tells us, all right, now we are on the, I don't know, it'd be like text side of the embedding space. If you imagine what happens inside a neural network very geometrically, always think about them forming kind of like this mapping of, in this case, language, 768 dimensions. Obviously, we can't see it, but imagine them creating this mapping of a room, and then every word or every token has a position in that kind of world that it built that is closer to the things that it's related to and further away from the things it's unrelated to. So if attention, you could visualize it kind of like that. Again, given the context, you can move this embedding towards the text side because the sentence was like, she went to the Apple store and got the iPhone. And yeah. So then that's what happens in each head of attention. And I think I forgot to mention, we compute each head of attention. Again, think of one head looking for punctuation, one head looking for grammar, whatever. And then we concatenate them again. So now it's, instead of just different heads that look for different things, now it's a whole, like a whole vector that tells us, all right, the change of the position, and then that's what we pass to the next layer. The next layer being the MLP, where it kind of learns what's actually going on. And yeah, that's pretty much how these LLMs learn to, learn their language. So you guys can train it yourselves. I think Gabe said he was going to send the final thing, like the final notebook. If he doesn't, I will. Again, lower the steps because I tried to train it myself and it was going to take me 9 hours. So I'm like, never mind. But you can train it yourself. You could also pass the code base kind of through Gemini in a way, see if there's any training improvements you could do to see if you could generate like an actual, something that makes more sense past the first sentence. Next workshop. Oh, and I forgot to mention here, if you guys want to add this to your resume, this would be how I would describe the bullet points. So yeah, and I will make sure to send the final notebook. This is for our Wednesday meeting at 2:30 in OAIHAN. We're gonna go over post-training. So how do we move on from just something that generates text? And it's pretty cool, something that by itself generates English, but how do we make it into like what we have now, like a chat bot that actually responds to you and is helpful in a way? It's an assistant. We're gonna go into post-training. I think I'll make it like a pretty short lecture, probably like 45 minutes to an hour, not the full length. And next week, we're gonna build an image generation model from scratch. So that should be pretty cool to kind of end it off for the semester. Next Monday, we're gonna learn how image generation works, and then Wednesday we build it. So yeah, yeah, next Monday, next Monday, learn how image generation works. Next Wednesday, project, and I'll try to make it as cool as possible. And yeah, so thank you guys so much for coming. Let me end the recording.